welcome to our last new lesson in the course. I plan to do some sort of review video for the final exam next time, come out later in the week. But now we're discussing area between curves. So we've talked about area under the curve for a while using the definite integral. But now we've got two curves involved. Well, let's say they're f of x and g of x, and g of x is the higher one in terms of y values. On some interval, the x is between a and b. So then the area between the curves it comes from some definite integral, but the integrand here is g of x minus f of x. The higher one minus the lower one, dx. So if I draw a little picture here, okay, so let's say that here's x equals a, here's x equals b. Well, on this interval, g of x is higher than f of x. And to find the area in between here, well, you would use little rectangles like with Riemann sums that we did before. It's just that now this height, instead of the full g of x, well, it's shorter. It's g of x subtracting off that height from f of x. So think of this as the height of your rectangles if you're doing a Riemann sum. And dx is like the width. And this integral sign is like a sum. You're adding up all those rectangle areas. This is just taking the limit as the number of rectangles goes to infinity. That is, you get a perfect approximation of the area. So let's find the area between the curves. X equals -2, x equals 1, y equals 2x squared plus 11, and y equals 1. Now it would help to get a sense of what's going on here with the picture. So first I notice I'm stuck between these two x values. These quote-unquote curves are vertical lines. So -2 and 1. And next, y equals 2x squared plus 11. That's a parabola shifted up 11 units. And that times 2 just means it's a steeper parabola. So won't get too precise here, but suppose 11 is, might want to make that a little lower for the sake of the picture. Okay, it'll keep going. They'll connect. And then y equals 1. That's a horizontal line at height 1. Say it's about here. So we're trying to find this area. Well, I have my limits of integration, my x bounds, if you will, between x equals -2 and x equals 1. My higher curve is the parabola, so I write that first. 2x squared plus 11. Subtract off the lower curve, just 1, dx. So now we simplify. 2x squared plus 10 dx. And now we apply the fundamental theorem of calculus, where we find the antiderivative of this thing and evaluate it at these endpoints here. So I add 1 to this power of x. That's 3, then divide by 3. So 2/3 x cubed plus 10x, evaluated from -2 to 1. Remember, you don't need a plus c here because for the fundamental theorem, when you're finding an area like this, it doesn't matter. You'll get the same thing. So remember this, we plug in the top number first and then minus plugging in the bottom number. So 2/3 1 cubed plus 10 times 1. Then minus, now plugging in -2. So we get 2/3 plus 10. All right, so here, this will be a -8 times 2. That'll be a -16 over 3. Then minus 20. How about we distribute that negative now, this minus? So, well, that's a double negative first. That'll be a plus 16 over 3. Again, we have a double negative here. So plus 20. Now let's bring those fractions together. That's 18/3. Hey, that's a nice number, actually. And the 10 plus 20 is 30. That's 6 plus 30. Get a nice answer of 36. So that means that 36 little 1 by 1 blocks will fit into this area. Next, find the area of the region bounded by the graphs of y equals x squared and y equals x plus 6. So this time I'm just given 2 normal curves. Well, let's get a sense of what's going on based on the graph. Whoops, just a rough sketch here. So we've got a standard parabola, y equals x squared. And then I've got a line of slope 1 and a y-intercept of 6. Let's say that's up here. This gives us a rough sense of what it looks like. Talking about this area. So first thing to note is which curve is higher on this interval. Well, that would be the line. It's higher up than the parabola. So note that x squared is less than or equal to x plus 6 on our interval. Of course, that changes elsewhere, but we're only concerned about this little region here. So next, I want my limits of integration, the x values that I integrate between. Well, how do we find those? So to find the limits of integration, notice that that's going to be where these two curves intersect. So we find the intersection points, in particular the x values where they intersect. Again, we really only need the x values. So we set them equal. We set x squared equal to x plus 6, and then solve for x. This is quadratic because of that x squared. These are easiest to solve if you move everything over to one side. So minus x minus 6 equals 0. And then factor. That would be minus 3 and plus 2. So this means x can be negative 2 or 3. And these give us the x values that we're integrating between. So we are solving the definite integral from negative 2 to 3. Write the higher curve first, that would be the line, minus the parabola. So now we're set up, and now we can just solve this definite integral. So I might just clean this up on the inside first. I like to write higher degree terms first. Plus x plus 6. All right, now we take the antiderivative. And we evaluate. So negative 1/3 times 3 cubed. Right, plugging in 3 here. Then minus, now we plug in negative 2. Plus 6 times negative 2. All right. Well, here we get a little canceling. This 3 with one of these. And that's times negative 1, so we'll get negative 9. Here we'll get 9 over 2. That's plus 6 times 3, 18. And, all right, let's still just deal with this parenthetical part internally. So negative 2 cubed is negative 8. And that's also times a negative. So it becomes positive 8 over 3 in here. Here, this will be a positive 4 divided by 2. Okay. Then minus 12. And I still haven't distributed this negative yet, so we'll have to do that. While I'm at it, I can combine this negative 9 and 18 as well. So that'll be 9 plus 9 halves. And now we deal with this part, the parentheses. Negative 8 thirds. So inside here, this is negative 10. And then I'm taking the negative of that. Let's add those whole numbers together to get 19. And we'll have to get a little more creative at the end here. If we're adding fractions, we're going to need a common denominator. So the best way to make that work is to have these both be over 6. 2 times 3. We'll go ahead and do that with the 19 as well. Make that some number over 6. So I'm making this something that's all over 6. 19 times 6 is 114. So for this 9 halves, we're multiplying by 3 over 3. 9 times 3 is 27. This 8 thirds will need to multiply by 2 over 2. That's minus 16 over 6. And so we get an exact answer of 125 over 6. That does not reduce. Next. Let's find the area of the shaded regions, and now I'm going to graph this. Okay, so some curve like this crosses at the x-axis at 1. And let's say we go out to 2. So that's where we stop. So notice we have a lower portion, a portion that's below the x-axis, and a portion above. Well, when it says find the area, we're thinking of area as a positive thing. So this lower part, I do not want to count that as negative. Oh, and by the way, this curve is y equals e to the x minus e. We do need to know that for this problem. So y equals e to the x minus e, that's the curve I drew here. Well, you could think of it as there being another curve here, namely y equals 0, the x-axis. And at least on this first portion, that is the higher curve. That's the top. And the bottom is this curve, y equals e to the x minus e. So we're going to need 2 separate integrals here, because notice they switch roles after 1. So between x equals 0 and x equals 1, 0 is on top, y equals 0, minus the lower curve, e to the x minus e. That just gives me this lower area. And then from 1 to 2, now e to the x minus e is the higher one, and the x-axis, y equals 0, is the lower curve here. So whenever you have a point where you're crossing the x-axis like this, you're going to have to split into two separate integrals because the role of top and bottom curve reverse. Okay, so we get, let's clean this part up. Got a double negative for the just e part, then minus e to the x. Here it's the reverse, e to the x minus e. So now we're set up and we just need to solve. So antiderivative of e is e times x. Remember, e is just a number. Antiderivative of e to the x is itself. Evaluate from 0 to 1. And then over here, now it's e to the x that's first, minus e times x from 1 to 2. So plugging in 1, we get e minus e, then minus plugging in 0, get e times 0. Well, be careful here. E to the 0 is not 0, it's 1. So that was just this first part here, the area of that lower portion. Now over here, first we evaluated 2. So e squared minus 2 times e. Then minus plugging in equals 1. Well, that is, again, e minus e. So that part will be 0, as is this beginning part here. So what's left? Well, I've got a double negative for the 1. So that's a positive 1. And e squared and minus 2e. So that's an exact answer, but Pearson will often ask you to approximate. So we'll do that to 3 decimal places. Should be about 2.952. So almost 3 square units will fit in that shaded area. Now, find the area of the region enclosed by y equals x cubed and y equals x. Okay. Well, which one is the higher one? Which one is the lower one? And the answer is that it depends. Depends on the picture. So let's try providing a rough sketch. I'm going to go down here. x cubed looks like this kind of. And then you also have the line y equals x, just this perfectly diagonal line passing through the origin. So you have this little switcheroo going on. When we're on the left here, it's the x cubed curve that's on top. That might be easier to see if I just shade with a different color. Or like this. So on one side, x cubed is on top. On the other side, it's the line that's on top. So we're going to have to split this into two integrals. And perhaps it would help to figure out where are the points of intersection first. That will help us with our limits of integration, those x bounds. So intersection, where do these curves intersect? We'll set them equal, x cubed equals x. Be careful. Do not divide both sides by x, because you're not allowed to do that if x is 0, let's say. And so in that case, we would be actually missing out on one of those intersection points when x is 0. So what you really want to do is subtract x from both sides and then factor out x. And then you can factor this one too. So we can see that the intersection happens when x is 0, when x is 1, or -1. So how about we write -1 first, since that's lower. So this is the middle point when x is 0. That's where the switch happens, where there's a reversal in roles from which curve is on top. So for x between -1 and 0, that would be the left side here. Well, the line y equals x is lower than the cubic polynomial x cubed. But then it switches from 0 to 1. Now y equals x is higher. So we will need two integrals from -1 to 0, x cubed minus x dx. Then from 0 to 1, x minus x cubed. All right, so let's find those antiderivatives. I get 1/4 x to the 4th minus 1/2 x squared from -1 to 0. And over here, I get 1/2 x squared minus 1/4 x to the 4th. Maybe we can save a little time by recognizing this whole thing is 0 when I plug in 0 for x, right? You have to be careful and really check that, but that's true when it's just x to the 4th and x squared. So then minus, plugging in -1 now. Notice that all my powers are even, so it's going to behave just like 1. The negative will go away. And now on this right side, we'll have 1/2 times 1 squared. Let's just call that 1/2. Minus 1/4 times 1 to the 4th. Minus, plugging in 0. Well, again, that's going to be 0 for both terms. So here I get 1/4 minus 1/2. But this whole thing is negative, isn't it? Well, maybe we'll do this one step at a time. Plus 1/2 minus 1/4 over here. All right, well, with this negative out front, that's going to be really the same thing. We'll have a positive 1/2, so I'll just go ahead and write that first. And a negative 1/4. And that's what we have over here as well, 1/2 minus 1/4. Now we can find a common denominator by putting this all over 4. So 2/4 minus 1/4 plus 2/4 minus 1/4. Well, this is 1/4, and so is this. So altogether, that is 2/4 or 1/2. So that is the total area between x cubed and x here. Half a square will fit in there. All right, let's do one more problem. Let's just mainly focus on setting this one up instead of doing all the calculations. So set up the integral, or perhaps plural. Set up the integral or integral for finding the area between y equals 2 e to the 2x and y equals e to the 2x plus 1. And we'll give the x bounds here from x equals -1 to x equals 4. Right, so we know that we are in between -1 and 4 with our x values. However, it's still possible that we might need more than one integral here, because it's possible that they might cross in the middle. And then in which case, what was the top curve now becomes the bottom on the other side, and vice versa. So we want to check first, is there some intersection point in here? Do they intersect on this interval? Well, we can find out by setting them equal. So 2e to the 2x we set equal to e to the 2x plus 1. We'll notice that if I subtract e to the 2x from both sides, notice I had 2 of these e to the 2x's minus a single e to the 2x. So what's left is just a single e to the 2x. equals 1. And we can take ln of both sides to get that exponent down. So this becomes 2x because ln has base e. So the ln and e part cancel each other. And ln of 1 is 0. That's true of any logarithm. Any logarithm of 1 is 0. Then we solve for x by dividing by 2. So these two curves we're talking about, they intersect when x is 0. Now, is that on our interval? Well, yes, we're looking between -1 and 4. So we're going to have to split this into two separate integrals, with x equals 0 being our transition point. So I want to put this in writing. This means that one curve will be higher from x equals -1 to x equals 0, but then they will likely switch. We'll have to check that. From 0 to 4. And those will give us our two separate integrals. So how do we find out which curve is higher on which little subinterval? Because these are both kind of complicated curves we're not really used to thinking about. Well, just try plugging in an x value on each side, and then you can determine which is higher. So we plug in x values to find out. So between -1 and 0, I want to pick a nice x value to plug in. Really, -1 is fine. It's okay if it's a quote unquote endpoint here, because this was really just an arbitrary place we chose to stop. It's not an intersection point between the two curves. So -1 is a nice number. That'll give us a good understanding of which curve is higher on the left side. So 2e to the 2x, we plug in -1. So that is 2e to the -2 power. You'll need your calculator for this. And I got about 0.271. Okay, then if we plug into the other function, e to the 2x plus 1, so that is e to the -2 plus 1, well, I get about 1.135. So clearly the higher number. That means that on that left side, for x equals, excuse me, for x between -1 and 0, the 2e to the 2x is the lower curve, and the e to the 2x plus 1 is higher. We found that out by plugging in at a test point. Well, now let's look at the other side. Between 0 and 4, that's our next integral. 1 would be a good number to plug in. So 2e to the 2x that is 2e squared, get about 14.778. And then e to the 2x plus 1, that is e squared plus 1, well, we get about 8.389. So that means the 2e to the 2x is the higher one here. For x between 0 and 4, the e to the 2x plus 1 is the lower curve. So they did switch. And now we know which one is highest on which side. Now we're ready to set up our answer. We have this left portion between between -1 and 0. And then the curves intersect at 0. And I'll just use brackets. Well, for this side, it is e to the 2x plus 1, which is the higher curve. So we write that first. E to the 2x plus 1. Then minus the lower curve, 2e to the 2x dx. Then the other side from 0 to 4. Now it's 2e to the 2x, which is the higher one. So it's that minus this whole thing. Well, I should use brackets, be consistent here. Or minus the whole e to the 2x plus 1 dx. Well, the problem only said to set up, so we're done. We could do the antiderivative of this one. It's doable, but that's it. That's all that we were asking for. All right. Well, that is it for the new content in this course. Later this week, I'll try to put out something that will be some sort of exam review. So see you then. Don't forget about exam 3 as well, if you still haven't taken that.